Around 10,000 BCE, before the first agricultural revolution, there were only a few million humans on Earth. In 1804 CE, there were about 1 billion of us. And just a couple of hundred years later, in May 2020, there's around 7.8 billion people living on this planet. It's getting a little crowded here. Our population is growing faster the more people there are. But how fast is it growing right now? How many people would there be by May 2050? Now, we could sit down and do the algebra to calculate the exponential growth and get precise predictions. But to see the big picture, the thing to do is, well, draw a picture. A graph. Looking at a graph, we can see how the human population is growing, determine the number of rabbits a habitat will support long term, or compare the GDP growth of different countries. Many kinds of crucial information are easiest to absorb with pictures. Today, we'll tweak the techniques we learned in our last 2 episodes on graphing, like employing symmetry and plugging in points to plot data, to graph just about everything else we might ever encounter in college algebra. G'day, I'm James Tanton, and this is Study Hall Algebra, presented by Arizona State University and Crash Course. It might feel like we've reached the end of our graphing by hand careers now that we're facing trickier things like logarithmic or rational equations. But remember how graphs of quadratic equations were all just fancier versions of y equals x squared? Once we find the core structure of these new equations, we'll see that we can plot just about anything. So let's start with exponential equations, equations where exponents are variables. As we learned in episode 7, exponential equations can take lots of forms. But the ones we use to model things like population growth all have a couple of things in common. For one, they're functions. So we can plug in x values and get just one y value. Something like -3 to the x equals 9 is an exponential equation, but it only has one solution, x equals 2. I'm not going to get a graph out of that. And second, the exponential functions we're interested in have positive bases. A graph of something like y equals -3 to the x will be full of holes, since not all x values are allowed without imaginary numbers, and it won't necessarily help us understand a real-life situation. So let's start by graphing our old friend y equals 2 to the x. Now, if we plug in easy-to-check numbers like 1, 2, 3, or 10 for x and solve for y, we might start to see a trend. Well, 2 to the 1 is 2, 2 to the 2 is 4, and 2 to the 3 is 8, but 2 to the 10 is 1,024. And if we keep going, 2 to the 20 is in the millions. Since 2 is bigger than 1, bigger exponents will always mean bigger y values. So we see that the graph of this equation rockets up very quickly as x increases. And we can plug in easy-to-check numbers on the other side of our graph too. Anything raised to the 0th power is 1. Great. The negative exponents move our powers of 2 into the denominator. So 2 to the -1 is a half. 2 to the -2 is a quarter. And 2 to the -10 is 1 over 1,024, and so on. Even if the x values are negative, the y values will always be positive, but they get closer and closer to 0 as x decreases. Now, our thinking here relied on our basic exponent rules, not the base. So all other exponential graphs will follow this pattern. Even if we tack on a coefficient, like with y equals 8 times 2 to the x, or y equals 2 to the x all over 2. For coefficients that are powers of 2, there's a neat trick involved that you might remember from the episode on exponents. 8 is 2 cubed. So 8 times 2 to the x is really 2 to the 3 times 2 to the x, which can be rewritten as 2 to the x plus 3, since we can add exponents when we multiply terms with the same base. Now all the action that was originally happening at x equals 0 is now happening at x equals -3. In fact, if we plug in -3 for x, we get y equals 2 to the 0, but the shape is still the same. Now with 2 to the x over 2, we can cleverly manipulate the exponent to see that it's really 2 to the x minus 1. And the graph shifts the other way so that all the x equals 0 action is now happening at x equals 1. But again, the shape is still the same. In general, multiplying by a constant is just multiplying the original y values by that constant. So for exponentials, that also means shifting the graph to the left or to the right. And if we change bases to something else positive like y equals 3 to the x or y equals e to the x, the trends we originally found stay the same. If we compare the y values, we'll see the same general shape, we've just adjusted the steepness of the curve. So, when graphing exponential equations, just find a simpler version of your equation and start with that graph, just like we did with quadratics. Now, everything we've done so far with graphing exponential equations is actually everything we need to do to graph logarithms. They look really weird, and something like y equals log base 2 of x is just puzzling to try and visualize. But remember that logs should really be called powers. The equation y equals log base 2 of x is just saying that y is the power of 2 that gives x as the answer. So 2 to the y should equal x. Aha! Graphing our log equation is the same as graphing x equals 2 to the y. And we just did that. Tilt our head a bit and we're done. It's just the graph we had before with the x's and y's switched. So now put the axes back to where we're used to and we can just flip the picture and ta-da! Y equals log base 2 of x. Any logarithmic equation will basically look like this. For x values smaller than 1 but bigger than 0, the curve heads down towards the negative y-axis as x moves closer to 0. And for larger and larger positive x values, the curve increases. just kind of slowly. So far, graphing other equations isn't much harder than graphing quadratics. The trick is the same. We're just transforming a basic shape over and over. So let's up the ante and look at rational equations. Why not? So let's start with the simplest one, y equals 1 over x. Now, if you don't know what the basic shape looks like, a good starting point is just to make a table of data points with some friendly x values like 0 or 10, just like we did for exponential equations. Usually, 0 is an especially friendly choice. But here, something immediately jumps out at us. X can't be 0, so a graph will not have a point on the y-axis. But knowing x can't be 0 lets us do something unusual. Let's multiply both sides of our equation by x, and now we've got x times y equals 1. Again, we can notice that x can't be 0. 0 times anything will be 0, not 1. But also, we can see that y can't be 0. There are no points on either axis. But we can still make a data table with other points. X and y just have to multiply to 1. So if x equals 2, then y equals a half. Same for x equals half, y equals 2. And x equals negative 2, y equals negative half. And x equals negative half, and y equals negative 2. We can gather lots of data points like this. There's lots of symmetry at play here. Basically, as x gets bigger, y has to get smaller, so that x times y is still 1. And if x is tiny, then y has to be huge. But all this without x or y ever being 0. The axes, the lines x equals 0 and y equals 0, are actually asymptotes, or lines the graph gets closer and closer to. So, when we put it all together, we can think of the points 1, 1 and -1, -1 as our corners. And on either side, the graph will be approaching its asymptotes along the x and y axes. And for the first time, we have a graph that comes in 2 pieces. So what if we had a more complicated rational equation, like y equals x plus 6 all over x plus 4? How could we uncomplicate that one? One approach is to do what mathematicians call engage in wishful thinking. Now, wouldn't it be lovely if the numerator were exactly the same as the denominator, and we could change it all to y equals x plus 4 over x plus 4? Well, we can't go that far, but we can get an x plus 4 to show up in the numerator. Just think of x plus 6 as x plus 4 plus 2. So now we have x plus 4 plus 2 all over x plus 4. And we can separate that into x plus 4 over x plus 4 plus 2 over x plus 4. That first term is just a fancy way of writing 1, so now we really have 1 plus 2 over x plus 4. The behind-the-scenes 1 over x structure is starting to appear. So let's go back to y equals 1 over x for a second. If we multiply that by 2, so y equals 2 over x, all the y values are double what they were before, and the curve stretches a bit. The graph of y equals 2 over x plus 4 is just the same, except the plus 4 in the denominator means that all the weird stuff that was happening at x equals 0 is now happening at x equals negative 4. That moves the whole picture 4 units to the left. And finally, adding 1 to the whole equation adds 1 to all the y values and shifts the whole picture up 1 unit. Now, if all that sounds overwhelming, please don't be dismayed. It takes practice to develop the intuition about how to find the basic templates hiding in more complicated equations. It's a literal learning curve. And building our skills by hand plotting functions is worth the effort. If we know how to make those connections, we'll be able to use our graphs to answer questions and even make important decisions. Let's look through some biology goggles. All biology goggles are really math goggles if you zoom in enough. Let's say you're a scientist studying algae bioremediation, which basically means you use algae to fight pollution. Ideally, you grow algae on the surface of polluted water. The algae then takes up the pollutant as they grow, and you skim the algae off and you have a less polluted pond. Repeat with more algae until the water is clean. Sounds great. And slimy. With just a few algae cells and plenty of sunlight, they'll reproduce super fast. But as soon as they fill the pond, they'll run out of light and their population is going to level off and stop growing. That's when they've reached their carrying capacity, or the maximum the environment can hold. Populations that grow super fast and then level off are common in biological systems. They're modeled by logistic equations, where A, B, and C are all constants based on data from past experiments. Logistic equations, like this one for your algae, make it hard to see the carrying capacity right away. But by plotting a few points to get a graph, the carrying capacity line is more obvious. And you can know when to skim off one batch and let the next batch start growing. You thought it takes about 2 weeks to level off, but to be sure, you plugged in X values up to day 21. Turns out when you check the Y values, the algae growth levels off much sooner, after about 12 days. And from there, you can work backwards to look at the X values and see if you could skim the pond any sooner. At 6 days, it's only about half filled, but the curve is almost level after 10 days, which would have been hard to find without graphing the equation. So you'll end up doing more bioremediation cycles in fewer days, and that's going to get your water clean a lot faster. So, will you graph everything by hand for the rest of your life? No way. But the training from the graphs you're drawing right now will be with you for as long as you need it. If all else fails, and you get stuck trying to predict what the graph is going to look like, don't get discouraged. Make a table of points. A table of X and Y values will never fail you, and there's no shame in doing this. After all, a graphing calculator essentially does exactly that. Next time, we'll finish out our discussion of graphing with some real-world applications of data fitting. Until then, cheers! Thanks for watching Study Hall Algebra, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video and want to keep learning with us here at Study Hall, be sure to subscribe. You can learn more about ASU in the videos produced by Crash Course and the links in the description. See you next time.